Swayam Prabha. Digital India. Educated India.
So to continue with this session, our next speaker is Dr. Achao Dong, and he is going to present on stochastic programming based mathematical model and solution strategy for chemical production scheduling with processing time uncertainty. So Dr. Dong, over to you.
Okay, thank you. Can you see my screen now?
Yes, we can see
Okay.
your screen and you are audible.
Okay, thank you. Hi, everyone. My name is Yachao Dong. I work in Dalian University of Technology in China. And I don't know if that's a coincidence or not. Previously, I did my PhD with Dr. Christos Maravillas, and today my talk is just after his talk. So I want to thank the organizer for the arrangement. Through this talk, I will present on behalf of my colleagues, Jinxin Gao, Dr. Lingling Liu, and Dr. Jian Du on our work on the stochastic programming-based mathematical model and solution strategy for chemical production scheduling with processing time uncertainty. My presentation will have 4 parts. After a brief discussion of the background, I will talk about the mathematical model and the solution strategy. And finally, a few words on the conclusion and future work. First, on the background, chemical production has always been a widely studied topic in the last few decades in the PRC community. It is important to consider uncertainty in the decision-making process because there are many different types of uncertainties, including the processing time fluctuations, sudden unit failures, emergency orders, and a few others in practice. Such uncertain factors will very often impact the original schedule, causing the issues of suboptimality or even infeasibility. And therefore, it is very important for us to take these uncertain factors into consideration when solving the scheduling problems. And how important is it to consider uncertain factors? Let's look at a simple motivating example together. In this network, there are 4 tasks, T1, T2, T3, and T4, producing 2 products, P1 and P2. And if we don't consider uncertainty and solve the problem of maximized profits in 12 hours, we can obtain this schedule 1, schedule 2. They have the same yield and the same profits. And they are shown in this table. However, in practice, there are uncertainties, as we said before. So we mainly address the processing time uncertainty. Therefore, let's suppose that task T2 has longer processing time. So we need to revise the original schedule a little bit to satisfy the real processing time. And in this way, we can see that the revised schedule 1, schedule 2, they are different in terms of the yield and the profit. Revised schedule 2 is better than schedule 1 in this table, and the difference is not small. Therefore, we know that it is important to have some sort of built-in intrinsic considering of the uncertainties in the scheduling model. And generally speaking, there are 4 different approaches to handle uncertainty in the scheduling problems, including robust optimization, stochastic programming, parametric programming, and fuzzy optimization. First of all, robust optimization, it produces a robust solution by imposing the constraints to consider the worst case scenario. And therefore, it is immune to the data uncertainties, but it may suffer from the issue that solution is sometimes too conservative. On the other hand, in stochastic programming, we optimize the expected value of multiple scenarios, and in this approach, uncertainty is shown as the scenarios with probabilities. For parametric programming, it's typically the uncertain parameter space is typically divided into subspaces, and this approach provides a solution as a function of the considered parameters. And finally, for fuzzy programming, it is very useful for the case where the detailed data of the uncertainty is not available. And therefore, for fuzzy programming, the uncertainty is shown as a fuzzy set. Considering that the historical data are often available to characterize the production environment uncertainty factors in the ERP or math system for schedules, we adopt the stochastic programming approach in this work. And the problem statement is as follows. We are given a set of tasks and a set of units, and the allowed task executions in each unit are given, and their batch sizes, the lower bound and upper bound are given. The set of materials, including the raw material to the intermediate to final products are given, and their material storage capacity is given, and the price of the product is also given. We are also given a set of time points determined based on the time horizon and the interval. We adopt a discrete time approach. The production recipe is given, which is a norm in every scheduling problem, and the fixed and variable costs are also known. We consider the uncertainty information in this work, which is the processing time uncertainty, and it is characterized by a set of scenarios C. And for each scenario, a given task has a processing time value, and the probability of each scenario is calculated based on historical data or other estimation. And the goal of our scheduling problem is to solve the maximization problem of the total profits. And in this solution, one should determine the optimal production assignment and the production sequence, as well as the batch size of each batch size and the optimal production time in each scenario. Next, we show the stochastical programming model. We have task allocation variable, binary variable, WIJTC defined here as in the classical discrete time SDM approach, but adopting index C here, denoting the scenario. And we define a new variable xij, and here it is not indexed by C because every task in each scenario should be of the same sequence. So it is 1 if task I is the nth task processed in unit J. And on the right, we show the relationship of the X variable and the W variable. And note that we use the executions of the tasks in the model. In this example, T1 is followed by T2 and afterwards T1 again. Therefore, the first batch of T1 is written as T1-1 here. That's how the relationship of variable X and W is. And here is our logical constraints for these two binary variables. They are written by using the big M type of constraints. And when both WIJTC and XIJN are 1, both constraints become active. One is greater than and the other is less than. So the constraints become the right one, requiring that before time t, there should be exactly n-1 tasks correctly executed. On the other hand, when one of the variables is 0, the required constraints become redundant. The other constraints we will go very briefly. First, we have scenario-based SDN constraints requiring only 1 tasks at a certain time for 1 unit, the batch size constraints, the material balance, and the storage capacity. And on the right, we have the batch size constraints requiring it to remain same over different scenarios. And finally, we have the objective function of maximize the expected value of the total cost, considering sale price and fixed cost and variable cost for the production. This is showing how the model performs for a relatively simple case study, which is the motivating example. And there are 6 scenarios considered, and in each scenario, tasks T1 up to T4 have different processing time and different probabilities. And the results is shown in this table. And we can see that we compare the stochastic programming solution with the adjusted nominal solution. Using stochastic programming, the expectation of profits improvement is 14%, which is quite significant. And the previous slide shows that the model works for simple networks. But in practice, the production network can be very complicated with more tasks and more units, with even recycling streams very often. So to solve the complex network, we propose the network-based decomposition approach. And the basic idea is to decompose the entire flow sheet based on the processing flow of the products. In other words, we want to have different sub-processes to handle different products with the minimum cross-flow streams. To achieve this goal, we have 2 requirements for decomposition. First, the sub-processes must include the tasks that can transform a raw material to a product. And the second one is that the tasks in the entire process must belong to one and only one sub-process. And therefore, we can see this example is decomposed into 2 sub-processes. One is for the production of P1, and the other is for the production of P2. And the cross-flow stream is this one from intermediate species S1 produced in sub-process 1, and it is used as the input for task T4 in sub-process 2. And after decomposition, we need to solve each sub-process separately while updating the inner connecting parameters of P and D, and then resolve iteratively. And that's the basic idea of the decomposition strategy. In its execution, we classify the different problems into 3 situations. The first situation is the most simple situation, where there's no shared units between sub-processes and all products are of the same profits. In situation 2, we add feature to consider different profits of the product, while in situation 3, which is the most general one, we consider the shared units too. And this is the solution process for situation 1. On the right is the algorithm, which could be simplified as 4 steps. The first step, we solve a sub-process, and the second, we check if it cannot provide enough common states to another process. And in step 3, we determine if all the sub-processes are solved or not. And last process, we check if all the states demands are satisfied or not. In situation 2, it is more complex in the sense that different products have different profits, and therefore their production should have different priorities. Therefore, we propose to use surrogate profit for the common state, which measure the benefits for producing the common states into the final product. We use this formula, phi denoting the calculated transform coefficient from the product P to the common state S. And this is calculated as the profit divided by its production proportion. And this is the first formula. We have a second and the third formula, slightly different. The second formula, we have total processing time considered, and in the third formula, we have the average processing time considered. And we tested all 3 different formulas against multiple examples, and we find that each of them could be the best in different cases. So therefore, we recommend that a decision maker can try all three of them in the solution process and pick the one that returns the solution that gives the most profits. Because for complex network, it is not clear which of the formula could give the best decision. And for the third situation, there could be shared units in different sub-processes. To handle this issue, we introduce a parameter called the occupancy of shared units. And we use lambda to denote this parameter. And it is one if a competing task from other processes is used on unit J at time point D in scenario C. And because the time limitation, I will not go into the details of the algorithm. And now we will look at another case study, which is of situation 3. And this is based on the classical literature. And we add uncertainty in this work. Consider that tasks T3 and T4 are subject to uncertainties in the processing time, which include 4 scenarios. For this case study, no feasible solution could be obtained after 2 days solution time. Sorry?
Can you please wind up in 2 minutes?
Okay. Without decomposition, you cannot obtain feasible solution after 2 days solution time, but using this composition, it could be finished in 3 iterations. And this is showing the model statistics. The gap is about 3 to 6% after 2 hours solution time by Cplex, and the results comparing the stochastical programming solution with the adjusted nominal solution is shown in this table. And we can see that the expectation is increased by 35%, leading to the overall more profits. And this work has been published this year in Computers and Chemical Engineering. And there are 2 conclusions we can draw. First, the STM-based stochastical programming model optimizes the production schedule by addressing processing time uncertainty, and we consider the maximization of expected profits, but other objectives could be incorporated in the same framework, such as minimization of the mixspan or cost or tardiness and so on. And second, we also proposed a network-based decomposition approach, and which can effectively provide high-quality solution by using less solution time. And for the future work, the integration of medium-term planning and short-term scheduling under processing time uncertainty should be considered. And such an integration is typically conducted in the rolling horizon fashion. And with this, one of the main problem is that the targets very often become invisible because the planning and scheduling have different horizons. And therefore, we should calculate the production abilities. And this is not easy for the stochastic programming based approach because there's uncertainties considered, but we are currently working on the approaches to address this issue. I will not go into the details here. And finally, I want to send an invitation. Dr. Fei Zhao and I are working together to collect articles for a special journal issue of Processes Journal, and the topic is machine learning and data-driven techniques for complex industrial processes. And the articles related to this topic are extremely welcome. With that, I want to thank you for your attention, and I will be very happy to answer the questions.
Thank you, Dr. Dong, for insightful presentation. So is there any question for Dr. Dong?
Hello, I am Darpan Sukra, Doctor. I am a postdoc here in IIT Madras. I have a question in network-based approach. You shown. I am trying to learn actually. Situation 1, 2 is very different than situation 3. So what is very crucial difference is there in your algorithm, which you have showed 3 algorithms?
Yes, yes. Thank you for the question. So situation one is the most simple one, and we assume that different products are subject to the same profits, and there's no shared units. So this is the most simple case, and we can prove that the proposed approach provides optimal solution. When the problem is more complex, where there are shared units, there are different profits. We use some heuristic methods to calculate the surrogates profits, as well as we calculate the occupancy of the different units when they are common units used for various sub-processes, and through iterations we can obtain the solution, stochastic programming-based solution for the situation 3. This is based on situation 1, but we cannot prove that it is absolutely optimal in the sense of mathematics for situation 3.
So is there any question for Dr. Dong? So I have just one query, Dr. Dong. So you have used this uncertain processing time. So is it a fixed uncertainty, or you have used a distribution of uncertainty?
It is based on scenarios. If there's a distribution, you can granularize it and generate it into different scenarios to solve it in that sense.
Okay.
I hope that answers your question.
I was asking whether you have used the distribution of the processing time, or is it a fixed increased or decreased value when you are saying the uncertainty?
The uncertainty is it can follow certain distribution, and you generalize it into different scenarios.
Okay. All right. Thank you.
Thank you.
So let us thank the speaker one more time.
Thank you.
Thank you, Dr. Dong.